I'll show you just a set of basic connections or basic identities which connects different matrices if one matrix is produced from the other by doing elementary row operation. And if you know this elementary identities, finding the determinant, I mean, it will give you another way to find the determinant. First, you just reduce your matrix to the row echelon form and then start from there. For that, to present you this elementary identities, I will use this notation. Look at this. I'm going to use a symbol A for the matrix. And because I'm going to operate on rows of that matrix, I'm going to give names to the rows of that matrix. It is similar to what I did when we discussed with you diagonal matrices during the last lecture. With a minor difference though. In that lecture, I put the rows R1, R2, R3 in a column, whereas this time I'll put it in a row, like this. It shouldn't be too much confusing. It's just because if I make like a rows, if I put R1, R2, dots, then Rj, then dots, then Rk, then dots, then Rn, it will take too much space. That's why I prefer to put it in line. But I hope in your head you can still make this adjustment that these symbols, they represent rows of my matrix A, even though it's set in a line. Because it's a shorter, I mean, it will take less space on a slide, and that will let me fit all of the identities on one slide. So we don't have many of the row operators. We have only 3 of, I mean, here I have 3 listed. First one was something which we call row reduction. That's the main working identity operation we used most of the time when we do Gaussian elimination. So if I want to encode row reduction in this notation, it's something like this. It's if I take A with rows like this, and if I have a scalar, say lambda, complex number in principle, my B, which is a result of the row reduction, is a matrix like so. Look at this. First row, the same, all of the others the same. Jth row, you see, it is the old jth row plus scaled kth row. All of the other ones identical. Kth is the same, nth is the same. It's my encoding of the row operation, something you've by now done so many times, you know it even better than me. Now, the identity which you have to remember when you deal with the determinant is this. If one matrix, like B, is obtained from the other by row reduction, no matter which scalar is involved in that row reduction, determinants of both of them will be identical. So row reduction doesn't change the determinant. That's the first thing we have to remember. Second elementary row operation which you have in your tool chest is the row scaling with, again, some scalar lambda. In that case, you require, of course, that the lambda is non-zero. And if I want to encode this row scalar in my notations, I will write something like this. So you see, all of the rows are identical except for the jth row, which I scaled by this number lambda. So if you're scaling one single row, remember this, it's an important point. You sometimes, actually, it's rather often that people forget about that. If you scale only one row, determinant will be scaled accordingly. So this determinant of B will be lambda times the determinant of A. In particular, if you scale the whole matrix by lambda, not just row, but the whole matrix, means that you scale every row by lambda, the determinant will be scaled by lambda to the power n, because you did n individual scalings of each individual row. Row swap. If I would like to encode my row swap in my notations, I will write B matrix like so. You see, my k row went into the position of the jth row, and the jth row went into the position of the kth row. Row swap, it's another elementary operation which we have in our tool set, and in that case, that's exactly what happens to the determinant. Determinant changes its sign to the opposite one. Well, the final thing which you have to remember is this. The final thing which you have to remember is this. I will just open it. If you have reached the row echelon form by doing your elementary row operations for the square matrix, we just remember determinants, they exist only for square matrices. We don't even try to define determinants for any other matrices. If your matrix is in row echelon form, then finding the determinant of such matrix is very easy. You just factor all of the diagonal entries. That's a nice excitement about that, yes. Actually, you can see here the connection with my previous slide, with my Cramer's rule, because if you have a row echelon form of a square matrix, if you have such a row echelon form, you consider two possibilities, like every column is a leading column, right? Meaning that every diagonal entry on that matrix will be non-zero, and meaning that the determinant of that matrix will be non-zero. If you connect this with the Cramer's rule, which says that the determinant non-zero corresponds to the unique solution, is your loop just closed. Row echelon form having all leading columns on the left-hand side, it's a unique solution. Row echelon form having all leading columns on the left-hand side, meaning that the diagonal entry is non-zero, meaning the determinant is non-zero, meaning that you have a unique solution again via Cramer's rule now. Is a link, circular connection. Well, I have here what I called 5 star, 6 star, 7 star, meaning I think I put the star for the reason that they're not the main properties. They're more like a corollaries of these 4. You can easily derive them from these 4. Let's just see what I said here. I said here that if you have a matrix with a 0 row, determinant of such matrix will always be 0. How do I see that? Well, it comes from this property, for instance. Because how we can derive this identity from the number 2? You can do it like this. If you have a matrix with a 0 row, you can multiply this matrix by any number. No. Yes, you can multiply by 2, for instance. By you can, not the matrix, my apologies. You multiply this row by 2, you can multiply it by number 2. What's wrong with that? Nothing wrong with that. If you do that, on one hand, the determinant will double. On the other hand, it will be the same matrix because multiplying 0 by 2, it will be 0 vector. And so the determinant should not change. So on one hand, this unknown number, the determinant, it will double. On the other hand, it will not change. Only one number possesses such a property. If you double it, it doesn't change. It's a 0 number. That's why this will be 0. The 6th one, what does it say? I'll just say. The 6th one says if I have matrix with identical rows, you see, in the kth and the jth position, I put the identical vector, identical row. And then of such matrix, determinant will also be 0. How do we see that? Well, we see it via 1 and 5 star. Because if you have identical rows, you can always subtract this row from this one by doing row reduction, which will effectively achieve 0 row here. And on the other hand, which will not change the determinant. But having 0 here means the determinant is 0, and that's why you have 0. Finally, well, it's the one which I already discussed with you. If you scale the whole matrix by a scalar, you just multiply the determinant by the power n, which is a dimension of your matrix of that scalar.